Hi, everyone. We're just waiting for people to get into the Zoom room, and then we'll get started. Oh, great. I think we're at critical mass here, so we'll get started. First off, welcome. Thanks, everyone, for attending. My name is Elliott Chorn. I am VP of Markets and Technical Services here at Amperon, and I'm joined today by Dr. Laura Reed, Head of Product Strategy at Upstream Tech. Today, we're going to be presenting Weathering the Storm, Advanced Forecasting for Hydro, Solar, and Wind Assets, brought to you by the partnership between Amperon and Upstream Tech. As we get going today, I think it'll become very apparent why Amperon and Upstream have formed a partnership to help bring our solutions to our joint customer set. A couple pieces of housekeeping before we get started. There will be time later for Q&A, so please submit your questions via the Q&A button at the bottom of your Zoom screen. Also, we will be following up with slides and a video of the presentation for those of you in attendance today, as well as anyone that couldn't make it today. With that, I think we'll go ahead and get started. So today we're going to be talking about extreme weather and its impacts on renewable generation, specifically wind, solar, and hydro. As you can see from the map, there's a wide range of renewable generation sources, each of which presents its own challenges for forecasting and operations, particularly during extreme weather events. Amperon and Upstream formed our partnership about a year ago due to our overlap in the power market space. Our similar approaches, tweaked for specific use cases, made this partnership a no-brainer for us, which allows our customers to benefit from bespoke solutions for their specific challenges. A little bit about Amperon. Brief introduction for both Amperon and then Upstream Tech. At Amperon, our mission is to forecast the energy transition by empowering our customers to shape the future of every electron on the grids globally. We do this by focusing on the intersection of power markets, weather, and time series data, applying the latest and greatest AI and data science methodologies to analyze and forecast solar generation, wind generation, demand, and price. We do this at both the grid level and at the individual asset level, whether that be a solar farm, a wind farm, or an individual meter.
Great. And at Upstream Tech, we are similarly mission aligned. So folks, we've got about 30 to 40 folks on our team. And really our goal is to make weather and water data actionable. So we build models and products that are suited to help folks manage water and land. And the specific product that we've built for the renewable sector and for energy and water folks is HydroForecast. And essentially, HydroForecast blends the latest advancements in hydrologic literature and science with the power of machine learning. And what we've done is essentially put those two things together to build a streamflow forecast that can help folks in the energy and water space manage their resource. We consider this an example of narrow AI, where we're using AI to solve a specific problem. And our customers range from folks in the energy sector to really anyone that manages water. So just kind of putting those things together, and as Elliott said, our partnership, makes more and more sense as we think about our joint customers who are folks managing resources, trying to add renewables and meet the growing energy demands. And one of the challenging things for our customers and also for the models and products that we build is extreme weather and the types of consequences that these types of extreme weather events can bring. So we'll kind of walk through some of the challenges, both on the hydro side and also then the wind and solar side, and why these are important for us as we are building models and providing services to help folks manage through these difficult events. So the first thing, just setting a little bit of as the stage here, this plot is showing extreme weather events or disasters that cost over $1 billion in damages. So every line is a year. This is looking at the last 44 years. And the last 6 years get special colors. And that's to highlight the fact that these disasters are getting even more expensive. And so cost is one of the reasons that extreme events are such a challenge and so important to our customers is, we're trying to help folks who are trying to keep rates low. And when you have to, pay for the aftermath, if you have infrastructure that's been damaged or, societal impact wide, these types of disasters are really impactful. So on the hydro side, we have a couple of different what we call extreme events and mechanisms that bring these extreme events. I'll start with high flow events. So this is a time when you get a ton of rain or snow, something that's bringing a weather system through that is going to impact the ability for a hydro operator to optimize for power. So hurricanes are one example, one phenomenon that creates a lot of water, also a lot of wind. And over the last 30 plus years, we see the strength of these hurricanes, at least in the North Atlantic, kind of ticking upward. So fewer category 1s and category 2s and more category 3s and 4s. And these can bring, a lot of disruption to river systems where hydro is most active. On the right, we have atmospheric rivers. So atmospheric rivers are actually global. In the United States, I think we focus on California, where over half of California's annual water supply comes from atmospheric river events, which are these essentially systems moving through the ocean, dropping deluges of water in certain areas. And it can be a good thing because you need that supply, but depending on their location and if they are back-to-back systems, they can cause a lot of challenge with managing these high flow events. On the flip side, we've got the highs and the lows in hydro, and we've got droughts. So droughts are, it's a really interesting phenomenon, even mentally, where the challenge is like, I'm not sure when this is going to end. This is a prolonged event that I don't even know if I'm in a drought, but then it becomes apparent that you are, and really the impact of that is a reduction in the available generation that folks are producing. We're seeing this in the Pacific Northwest, which is the highest capacity area in the US for hydropower. We're seeing this prolonged drought, which has been over a decade long, really impact the bottom line of generation. And so just kind of putting those two things together, one of the reasons that this creates challenges for energy production specifically is that, at least in the US, most of our reservoirs are multi-purpose. So on the left, this is an image from the DOE Oak Ridge Lab showing that for all the hydropower dams, you've got multiple purposes that are also needing some attention. And if you're in extreme condition, like you are in a flood stage, flood control is going to take over at that point. In a drought stage, you're still going to have to pass minimum flows for certain constraints, recreation, fish. And so that really limits your ability to focus on optimizing for power, because instead you have to treat these acute issues. And so that's one of the reasons that with more extreme events and more disruptions, that creates, challenges for folks who need to manage and are trying to provide this safe, reliable power from the grid. And with that, I'll pass it over to Elliott.
Yeah, so first we'll tackle solar. In 2024, global solar capacity surpassed 2 terawatts of power. Within the past 2 years, there were more than previous 68 years combined. So we're seeing an exponential growth in solar. Optimizing these solar plants to meet demand is becoming increasingly challenging for a variety of reasons. These include, but are not limited to, smoke from wildfires, low cloud coverage, storms with wind, hail, or snow causing degradation or damage to the panels themselves. And then finally, maintenance issues, dust, soiling, snow, contributing to, again, degradation in performance of these panels, making it more and more difficult for the operators to then forecast what they're going to be generating and then matching that to demand on a given day. This is particularly difficult on overcast days when you have more artificial lighting occurring, where at the same time you have lower generation being produced by these solar panels. Going forward, we'll talk a little bit about a case study that Amperon did with AMO, the Australian energy market operator, during the summer of 2019-2020. There were, if you remember, there were brush fires that burnt more than 180,000 square kilometers of forest and grassland and sent giant plumes of smoke into the sky. Through our collaboration with AMO, the Australian energy market operator, we examined the effect of smoke plumes had on large-scale photovoltaic solar farms across Australia. We looked at data from about 20 different farms, looked at several different sources of solar radiation and irradiance, the intensity of smoke, and ran counterfactual simulations to assess solar generation. And what we found was that during December of 2019 and January of 2020, there was an average decrease of about 4.1% per plant, which could be attributed to the smoke plumes. We saw that ranging as high as 12%, given the proximity to those smoke and fire. But the average, again, was about 4%. So you can see how that would have a large impact on the performance of the plant during this kind of extreme event. And then talking about wind on the next slide, sorry. Wind growth continues to grow. Consistent growth in wind generation projected of about 11% increase. DOE is projecting about 400 gigawatts of total wind capacity across the 48 contiguous 40 states by 2050. Much like solar, wind has several factors which impact performance. Wind is much more difficult to forecast due to the variability of wind speed. Wind patterns are influenced by a number of things: temperature, pressure, topography, and seasonal changes. And these patterns change very quickly. Rapid variability of wind really forces you into a sub-hourly or 5-minute forecast to capture the rapid shifts. This granularity allows for more confident bids in the day-ahead and real-time markets for our operators that are forecasting and then financially responsible for these impacts. Now we'll move on to talk a little bit about how each of our forecasts handle the extreme weather that comes up. Starting with Amperon. Amperon, we combine asset metadata, historical generation data, weather, and physics-based model outputs using the Amperon AI engine to produce our asset renewable forecasts, which are available both on the Amperon platform and programmatically via our API. As I said earlier, we really focus our attention at the intersection of energy data, energy expertise, and weather data. And so you can see on the left there that we're ingesting all of the energy-specific data, as well as the historical generation and historical weather data into our AI engine, which is then able to produce our industry-leading forecasts. One of the ways that we generate accuracy is through our focus on weather data as an input into our modeling capabilities. We start with the geographic territory we're forecasting for, select weather points based on density and geographic proximity, acquire forecasts from multiple vendors, which are then ensembled together and updated on an hourly basis. This is a real part of where we get our cutting edge accuracy, is through the way that we handle and weight weather data. We're not taking typical airport weather codes and then using the data from that. We're buying hyper granular weather data, which allows for us to place multiple weather points within, an 80 megawatt solar farm to then further capture how cloud cover is moving across that, what other impacts there might be throughout the day. Another way that Amperon helps to generate accurate forecasts is through our combination of physics-based modeling and cutting-edge machine learning techniques. As you can see, each of these techniques has its own individual strengths and weaknesses. Machine learning really struggles with curtailment, which is when the solar or the wind facility is forced to shut down due to transmission constraints on the grid. Whereas on the other hand, physics-based models do a very good job with that, but struggle with partial asset metadata or biased weather. So what we do is combine those two into our final answer, our final deterministic value, which captures the strength and mitigates the weaknesses of each of these models. The next couple slides, we'll take a look at the Amperon product and some of the features that it brings to bear. This is our solar sub-hourly forecast that goes out 15 days into the future. We look at both historical and production layers, so you can look back, see how the model has been changing over time. And then again, we go down to that 5 minute of granularity. On the next slide, we'll look at our wind forecast, where again, we see a slightly different shape as we're looking at a overnight production of wind increase. Again, we go out 14 days into the future, 5 minute granularity, and we're able to look at this both at a total view for an entire portfolio of assets, as well as look at individual assets within that portfolio. And now back over to Laura.
Great. Thanks. Similarly, to what Elliott was talking about with the wind and solar forecasts, hydro forecasts are the same thing, where we blend machine learning and physics-based approaches and kind of the power of each of those to make hydro forecast. And some of the aspects of our model that are really important for being able to forecast extreme events are listed here in this table. The first one, same thing that Elliott was talking about, weather forecast. So in the case where a model is only pulling in one single weather forecast, we are prone to those errors and uncertainties. And so that really limits the ability for the model to see things outside of what that one weather forecast is providing. So our forecast is driven with multiple weather forecasts to basically be able to hedge for some of that uncertainty and to train on sources that might be better at predicting certain extreme events than others. The second thing listed here is to be able to operate when an input is missing. So in most models, you need a consistent time series where you have a value per time. And basically to be able to operate when an input like a gauge goes out or a weather source goes out, we've built our model with a data augmentation approach that allows the forecast to make its prediction and make a reasonable prediction, even if it's missing an input. Happy to talk more about that later. And then the last two things here are really speaking to the ability to forecast something that is both outside of its calibration or training record, but also something that is physically realistic. So especially with hydro, we have water balance, and there's a hydrologic cycle that everybody saw in second grade that really governs some of the theories behind hydrology. And so to be able to have a model that can see something that hasn't happened before, but also not make a prediction that goes out to lunch is a really important component of a hydrologic forecast. So how do we do that with HydroForecast? I'll kind of walk through how we build our core model and then how we take that to specific areas. So just as Elliott was kind of talking about, we have a range of variables that go into what we call our core model. And those are things that you would recognize as being important for hydrology and land surface processes. So that's elevation, topography, soil types, as well as time series data that are influencing what's happening in the next 10 days. So everything from precipitation to humidity, and we also pull in some satellite observations. So we train a very, very large model to learn these things generally. And so if you have a basin somewhere and it has a certain topography and a certain temperature profile, it learns that, but then it also learns a different sort of topography and sort of characterization of a basin. And when you have a single model that has that flexibility to understand different conditions, producing different outputs, it's a really powerful thing for taking to a specific site where then you have observations where you can tune that model to local conditions and local things so that it learns those processes really well. And that's one of the powers of then, okay, we have this core model that's seen many things. It's seen things outside this single basin. And so when you have an extreme event, like a big rainfall or a drought, it's actually learned to see that same phenomenon somewhere else, and it can apply that learning in this particular condition. So what that results in, we have a couple of different horizons that we produce forecasts on. We've got a dashboard that allows you to go back in time, look at things with different units and in different ways to see the flow forecasts. as well as we show all of the inputs that go into the forecast in terms of weather. So we've got multiple forecasts, precipitation and temperature forecasts that go into the model. And that helps our users understand, where is this uncertainty coming from in our probabilistic forecasts. The bottom there is alluding to the satellite inputs that we use. So one of the things about this model is that it's able to see if there's a change in the basin. Let's say you have deforestation or reforestation, the model gets to see that in real time using its satellite images, and it has often seen that in another basin. So it's, again, using that learning from outside the basin to help make its prediction. On the seasonal scale, we're offering guidance that goes out 12 months at a daily time step. And really, one of the goals is to understand the likelihood of having a super dry season or a super wet season. So that deviation from normal can be helpful for planning energy hedging and supply. And then also, of course, the actual magnitudes where you can take this value projected out months ahead and put that into your optimization plan. And then the last piece is just kind of a more detailed case on how our model works when it loses information in real time. So especially when you have a high flow event, there are gauges, there's instrumentation in these rivers that can go out. And recently there was a hurricane where the gauge that informs this area blew out because of the high flow. And on the right there, you can see, our forecast is able to use the information as long as it's there, and then make a prediction without needing it and without doing something that would disrupt the kind of continuous flow of the forecast. So that can be a really important thing when teams are stressed during a critical event, not having to worry about what happens when data becomes more limited. Last slide here is more of a teaser slide of a new product that we are developing. So we're using our expertise in inflow forecasting combined with information about production to create regional zonal level hydropower generation forecasts. So the goal will be to produce a forecast that can be pulled in from an API of what the hydropower generation is for different size nodes and zones, starting with CAISO, but then expanding outward from there. So stay tuned for that. And with that, I think we are wrapping up here and are looking forward to the Q&A.
Awesome. Well, for those of you that have already submitted a question, thank you very much. If you have questions, please go ahead and submit them. We should be able to get to them. I'll go ahead and dive in first. Question is around what are the sources that Amperon uses for granular weather data, and how do we verify the accuracy of that data? We have a few different sources that we work with. We start with some of the big public models like the Euro, the North American model, the GFS. So we start there, and then we work with a number of ensemblers like AG2, DTN, Spire, that ingest all these big public models and then ensemble them together into a deterministic output. How we verify that, there's a few third-party verification sources that we rely on, as well as looking at how that data performs in our models themselves. So, the proof is in the pudding when it comes down to that. If we're able to ingest that weather data and it gives a lower May per mean absolute percentage error score than another vendor, then we would consider ingesting that into our set of weather vendors.
Cool. Maybe I can take the first shot at the next one, and then Elliott, you can follow up.
Tag team that one.
Yeah, sure. So for us, the question is about sharing more on the value of machine learning and AI for renewable forecasts. And because these models are trained in the past, why does this approach help in the future with a more unpredictable weather? And I think from the HydroForecast standpoint, that's exactly a challenge. So the way that we train our models is we actually use past weather reforecast, so not observed weather where the model sort of gets to see a perfect weather forecast. We're actually training it on those reforecasts of weather where all of those errors and biases are built in. And so the model is learning what it will do in operations given all the uncertainty and differences that it's seeing in the training. The other thing is that because of how we train a big base model, so yes, you might not have had this specific weather event in your basin before, but if you think about 500 basins times, 8 years of training at hourly time steps, that's a lot of data for the model to be seeing and seeing things that, may be happening in this basin, but could happen in another basin. And so it adds to the ability for the model to see things outside of that individual record. Elliot, what would you add to that?
Yeah, just to add on from the Amperon point of view, part of what we do is quickly update and refresh our forecasts. So as I was saying, we do 5-minute sub-hourly forecasts. Those models are running every 5 minutes. And so the new input data that's becoming available at each of those is the most recent generation data that's become available. We don't necessarily get new weather data every 5 minutes, but we do get new generation data. And so that changing pattern can be captured very, very quickly. Our models, particularly for those sub-hourly forecasts, are trained to look at more recent data through a stronger lens than some of the further back data. And so it's able to learn much quicker than if we were doing just like a simple regression style of technique.
Great. Looks like the next one is about HydroForecasts. Are forecasts available outside the US? Are there geographies where there's not enough data? Yeah, so our model runs globally. All the weather sources that we're pulling in, the satellite data, those are all global. And so we have built a global model and we are active in 15 countries, I think it is now. Certainly there are geographies where data is a challenge. The great part also about the base model is that you can go to a new place that if there's no observations available, you can use your base model to build predictions without additional observations and still make a good prediction. And we've done that across the world. We've done that even in California where you think there's enough data, but depending on the application, there are a lot of streams that are ungauged that also need detailed predictions. Cool. The next one is about, do you take into account global events to forecast locally? How do you incorporate INSO cycles into the forecast? Yeah, so a lot of those like weather patterns and global weather phenomenons, we are reliant that the weather forecasts themselves, which are running those global models, are picking up on at least the nearer term. So the atmospheric river and the kind of the cycles that come through tropical events, et cetera. As far as INSO, we have trained models for the seasonal scale that include INSO. And depending on whether that signal actually improves the forecast or not, we will include it. We do use some predictive weather on the seasonal scale, but again, we're doing a similar thing where we're verifying whether that source is actually adding skill to the ultimate forecast before we kind of just throw it in the model as another input. Thanks for the questions. I think the next, go ahead.
I got a question. Do we do alternative scenario forecasts or sensitivity analysis to try to capture climate change effects on solar generation? Not exactly is the answer. What we do is by ingesting all the different weather vendors that we do, we run a forecast for each and every one of those vendors. So each of the components into our ensemble gets its own generation forecast run off of that data. Then off of the ensemble, we then run a separate forecast so that we get a range of outcomes that could occur using these different vendors that have given us some of that sensitivity to try to capture any long-term changes that we might see due to climate change.
Great. The next one, what sort of models do you use to guide projection for seasonal? Is it climatology or dynamical seasonal guidance? Yeah, I can kind of follow up the last answer with something here. So for seasonal forecast, we are blending together climatology from the last 40 years with live forecasts from GEFS and also testing out things like GraphCast and GenCast experimentally for increasing that skill. One of the issues is that the weather forecasts themselves going out beyond a couple weeks are not always skillful. And so we are picking those kind of forecasts and sources as we find them to have skill. And then we have a way to blend the forecast and the climatology so that we get additional skill out beyond 60 to 90 days in some areas.
There's another question that came in that dovetails quite nicely with that one. Some of the global models are starting to produce longer term forecasts that go out 35 days. Any plans to incorporate those? I know what the answer is on the Amperon side. Curious what on the upstream side.
Yeah, absolutely. I think that ECMWF long range and, to the extent that some of these AI experimental weather forecasts are going out that far, we are definitely planning to test those and already doing so somewhat. Go ahead.
Yeah, much the same at Amperon. We're really excited about these longer range forecasts. See them as a real opportunity to bring a distinct product to market using our underlying generation and demand forecast models. Laura was much more generous with her description of some of the long-term models to date, but we're starting to see a real sea change as to what is available and what's possible, particularly with some of the new AI-driven weather forecasts.
Definitely. Okay, could you share a bit more about how HydroForecast operates during a natural disaster like a hurricane? Does that accuracy stay consistent? So yeah, I think I could dig in more on this example, but essentially the way that we've built HydroForecasts is to use what we call data assimilation, so pulling in observations when they're available. But the methodology that we're using for data assimilation means that if there's a value that looks wild, because sometimes gauges before they go out of service, or even if they don't go out of service, they can produce some kind of non-realistic values. We protect the model from using those values, and then similarly, when that goes out, we won't use the value. And we presented on this at AGU, so I can follow up with more information. But we've created a data augmentation method where we've trained the model with random missing samples. And so when you do that, it means that the model actually doesn't just learn to skip or forward fill with the last available value. It actually understands that your data might not always be there and you might not know which sources are going to be there. And I still need you to make a good prediction. And so we've spent a lot of time to make sure that that accuracy stays consistent by going back to our training of the initial model and pulling that all the way through. Elliot, I think
Looks like I got a follow-up question here. It sounds like Amperon's essentially generating its own forecast, and I'm going to translate that to be our own weather forecast. How do you validate this, and how do you have a comparison of the forecast and the outcome? We're not actually generating our own weather forecast. What we're doing is generating an ensemble of the results of each individual forecast. So taking each of the forecasts that we ingest from our weather vendors, we then run our forecast model on that. So our generation or our demand forecast model, and then ensemble those results together. So instead of ensembling the weather forecast together, we're actually ensembling our demand or generation forecast together. And then the way that we validate that is really, it all comes back to accuracy. So, for us, the be all end all is MAPE, mean absolute percentage error. And that's a calculation between forecasts and actuals. So we're constantly validating against actuals and trying to get our MAPE to be as low as possible without biasing the model in any one particular direction.
I think the last question, how can storm modeling be possible? I think for us, I think that goes back to the weather forecast. So if we are pulling in as many weather forecasts that we think and have proven have increased the skill of our hydro forecast, then that's how we're able to capture storms better, is to make sure that we have that fidelity in the inputs so that then there's less error as it propagates through our system to the outputs. And we have, again, like a publication on how a neural network like the one that we use can actually do better if you show it multiple inputs at once, so it can kind of understand and learn what to do with those inputs when they disagree and when some of them have errors and some of them don't. I'm not sure if that answers the question, but
Now, here's a good one. What type of computational setup do we use to do this? So at Amperon, everything we do is cloud-based. We're Azure partners with Microsoft. We run a very cutting-edge tech stack. We use specific databases that are designed for time series data. We use a number of publicly created AI ML packages using Python. Laura, curious to hear how you guys do this.
it's very similar on our end at Upstream Tech. So we're running on the cloud. We have packages that we're using to help with the data processing. We've essentially built the data pipeline, and that's one of the hardest parts, I think, of running an operational model, is to make sure all of your operational data feeds that you're pulling are working right, and that's working efficiently so that you can make predictions, especially on a sub-hourly, I can imagine, for you all, and even an hourly basis for us. But yeah, everything's running on the cloud and is produced through those systems.
Yeah, it's the old garbage in, garbage out problem, right? Makes those data pipelines so important.
Yeah.
Well, cool. I don't know if there's any last minute questions coming in, but I think we're coming to an end here. Laura, this was awesome. Thank you for taking the time. Thanks to everyone who joined for taking the time. Really appreciate the time and attention here. With that, I think we'll shut things down, and we will be following up with the slide deck as well as a recording of the presentation. Thanks again, everyone.
Thanks, everyone.